Okay, welcome again. We're going to look now at an example of using qualitative variables as predictors of in a multiple linear regression model. And we're going to do a quick example using car data, and it's what we call a toy data set, a data set only meant for us to practice. So we have the miles per gallon of a car, and this would be the response. We have the manufacturer, which is the qualitative variable that we want to incorporate, and engine size as a predictor. The code to generate the data is in Canvas under car data, car underscore data.r. In order to incorporate the manufacturer, we need to create a dummy variable. So in other words, we have two levels. We have to select one of the levels as a base and then create one dummy variable for the class, for the level that is not the base. We need to create only one because we have two levels. If we had more than that, then we need to create the number of dummy variables accordingly. So for instance, an example, we can do the variable mfd and select GM to be the base level. So we would create the Ford dummy variable, and it would be mf. Let's say we call it mfd, and it would be 1 if equal to Ford and 0 if else. In this case, the else means if the manufacturer is a GM car, so there's no more option. So in other words, the model to fit now will be equal to miles per gallon is equal to the y-intercept plus the slope for engine size plus now a slope for the dummy variable. Now, what does it mean that the dummy variable has a slope? That dummy variable can only be 0 and 1. So remember, dummy variables can only take two values, binary variables that take the values of 0 and 1. So so what happens really? When MFD is equal to 0, we are referring to GM cars. So what that means is that the model now is going to be the y-intercept plus the slope of engine size. And that would be the slope of the line for a car that is manufactured by GM. And when these dummy variable is equal to 1, then that corresponds to Ford cars. But if we multiply something by 1, it just stays the same. So we actually are adding something to the y-intercept. So we really are not changing the we're not changing the slope of engine size. We're just adding something to the y-intercept. We're adding or subtracting. So the beta 2 parameter is going to be the average difference in miles per gallon between a Ford and a GM car. And this will make more sense when we go and look at the example in R. But the idea, well, is that is this engine size and miles per gallon are inversely related, which means that as the engine size increases, the miles per gallon generally decreases. And of course, engine size is sort of a proxy for car size, and the larger the car, generally the less miles per gallon. But when we have the slope of MF, so when we have the dummy variable equal to 0, that means that the car is a GM car. So let's say this is the red line right here. So this would be the equation. So what happens is that when the dummy variable for Ford is equal to 1, then that changes only the y-intercept. It adds or subtracts something. So it adds to the miles per gallon or subtracts the miles per gallon. So that's the way the dummy variables work. Right? So let's work in the example in R so that we can actually see it in practice. The code that you're going to see is actually in Canvas, so you can download it and play it around. So we have the engine size, we have the manufacturer, and I've put those in vectors. and a vector for engine size, and a vector for manufacturer, and then a vector for miles per gallon, and put it together in the car underscore data as a data frame. Right, so first let's take a look at the relationship. Let's look at the relationship between, let's say, the two variables, engine size and miles per gallon. And I just want to take a look at the quantitative variables first. So we're going to do the plot function, and then we're going to go with engine size in the x-axis and miles per gallon in the y-axis. Okay, so let's see the mistake. So let's write it exactly as it is. And this is the plot that we get. Again, a negative relationship, and it looks pretty linear. So there's indication that a linear model can work really well. All right, so now let's take a look at the regression. So let's call it regression 1, and let's use the ln function using miles per gallon as the response and engine size as the predictor. Okay, sorry about this. And let's do data is equal to car underscore data. Okay, so let's run that. Let's take a look at the summary really quick. And this is what we see. As the engine size increases, on average, miles per gallon of the car decreases by about 1.78. So again, just shows a linear relationship. The variable is significant. Explains about 82% of the variability in miles per gallon. So we have a strong predictor. So now, what happens when we incorporate a predictor that is just a factor or a qualitative predictor? So first of all, let me show you how to check the type of predictor. So we're going to use now the class function. So use the class function to check variable type. Again, you can always take a look at the current data set and the structure that shows you the factor, but I wanted also to show you the class function so that you can actually just verify variables individually, or if you had to use it somewhere else. But let's take a look at car data, manufacturer, and it shows that it's a factor, so that's what we expected. Now another function that is useful when working with qualitative data is the levels function. The levels function shows the different levels of a qualitative variable. Okay, so we can do levels of car underscore data manufacturer, and then check the levels. We can see that we only have 2 levels for that particular variable. Again, this function is fairly useful, especially if you have a lot of different levels. And of course, in the structure, the str function, or if you just click on the blue arrow, you can see the factor with the levels. And it generally shows that on the first 2. It shows you it's 2 levels and the 2 levels right there. But it might be useful if you have a lot of levels and you want to take a look at them all. Something important about this is that the levels are ordered by the first letter. So because F comes first, then this is selected. So this is actually sorted by the first letter. And again, sorted by, if you have ties, then it would just go to the next one. But this is important in how R determines what is the base level. So let's keep that in mind for now. For now, forward is the first level that it finds. All right, so let's go ahead and include this variable as a predictor. So we're going to use model now, incorporating manufacturer as a predictor. So we're going to call it regression 2 and use the ln function using miles per gallon as a response, and engine size as one of the predictors, and also using manufacturer as a predictor as well. All right, so we're going to run that, and actually let's do a summary. And now you can see that we have the engine size. The slope changed a bit from the original estimate, but it didn't change a lot. Of course, the slopes change depending on the variables that are included. But now you have this new variable, manufact, and then GM. So what does this mean? Actually, this is a dummy variable. So let's think about it for a second. So the way that R, so let's talk about how R creates dummy variables. Well, first of all, R looks at the levels of the categorical variable. So R select, and again, I'm just going to say the ln function, not really R, but the ln function selects the base level based on the first element, and then just keep on here, of the levels function. Okay, so what that means is that Ford is going to be selected, is selected as the base level. Okay, so if Ford is selected as the base level, then GM is what needs to have its own dummy variable. So we need this GM level needs a dummy variable. So this is the dummy variable created by R. Therefore, is the dummy variable created. Remember, a dummy variable can only take the values 0 and 1. So these actually is 0 if the manufacturer is not GM. And this is going to be equal to 1 if the manufacturer actually is GM. So that's the way it works. So let's talk a little bit about the naming convention of the ln function use. So first of all, the way that the dummy variable is named is based on the variable name first. In this case, it would be, well, the name of the variable is manufacturer. And then followed by the level of the dummy created. In this case, this is the level GM. So in total, we have the variable manufact then GM because it is creating that dummy variable for manufacturer. All right? So that's the naming convention. Let's go now to the interpretations. So what, again, the interpretation for the engine size stays the same. So as engine size increases by 1, on average, the miles per gallon increase by about 1.8, or decrease by about 1.8, holding the manufacturer constant. What that means is, well, I mean, not mixing around, comparing GMs to Fords or things like that. But that's the idea. What about the manufacturer GM? How do I interpret this? Well, what this means is, on average, GM cars have about 1.60. Have about 1.66 miles per gallon less than the class that we selected as the base, which is Ford. So in other words, so let me write it here. On average, GM cars have about, let's say, 1.66 miles per gallon less than the class that you left out. It's always the base class, okay? And the base class is Ford, than Ford cars. So that's one. I mean, it doesn't have to be exactly that, but you get the gist of what the interpretation really means. Is the average difference between GM and Ford cars, and because the difference is negative, then that means that GM cars have, on average, fewer miles per gallon than Ford. So I hope that that makes sense. We're just going to go ahead and keep on with the example, and we're going to include now another predictor in the next video.